In this video, we are going to discuss eigenvalues and eigenvectors, which is our first lesson in Matrices 2. Matrices 2 is a topic in Diploma in Electrical Engineering. If you are new to this channel, I would appreciate if you subscribe to the channel and continued watching the videos online. Now let us quickly go through our example. This question is from June-July 2019 Diploma in Electrical Engineering Module 3 paper. And we are told to determine the eigenvalues and the corresponding eigenvectors of the matrix A is equal to this. Just a brief background information, eigenvalues and eigenvectors find application in problems involving coupled oscillations, such as vibrations in mechanical engineering or oscillations in electrical power systems. We are going to say AX is equal to lambda x. Here, A is a square matrix, X is a column vector or a column matrix, lambda is a scalar. If we take lambda x, the other side of the equation will have AX minus lambda x is equal to 0. If we now factor the column matrix X, we will have A minus I lambda x is equal to 0. Notice we have introduced an identity matrix because it is only possible to subtract a matrix from a matrix. Now, if we take the matrix A minus I lambda and we find its determinant, that is A minus I lambda, we find the determinant of that. This one we call it the characteristic determinant. If we equate the characteristic determinant to 0, that is A minus I lambda, we equate this one to 0, this will be our characteristic equation. Now, if we solve the characteristic equation for lambda, the various values of lambda we are going to get are our eigenvalues. So now we are going to substitute the various matrices in this equation or in the characteristic equation. We have A is a matrix here, which is a square matrix 2 by 2. I, we have said, is an identity matrix or a unit matrix which we have introduced because we can only subtract a matrix from a matrix. Remember, lambda is a scalar, so we need to multiply it with the identity matrix to make it to be a full matrix. Now, let us derive the characteristic equation in matrix form. We'll have A is 3, 1, 2, 4, minus, we can start with the lambda multiplied by the identity matrix. Because this is a 2 by 2 matrix, we're also going to introduce a 2 by 2 identity matrix. We find the determinant of that, and then we equate it to 0. Let us simplify here. So you have the straight line tells you that you are supposed to find the determinant. You are finding the determinant of 3, 1, 2, 4. Open this bracket minus. Here you have lambda 0. You have 0. You have lambda. And then another straight line to indicate that we are finding the determinant. Now let us subtract these two matrices. It will be 3. If you subtract lambda from 3, it will be 3 minus lambda. If you subtract 0 from 1, it will be simply 1. If you subtract 0 from 2, it will be simply 2. And if you subtract lambda from 4, it will be 4 minus lambda. And remember, you're equating that to 0. You're finding the determinant. So how do we find the determinant of a 2 by 2 matrix? Multiply the element in the leading diagonal and subtract the element in the minor diagonal. So this is a leading diagonal, this is a minor diagonal. So here we have 3 minus lambda multiplied with 4 minus lambda. Subtract 2 times 1 is 2, you subtract 2, and then you equate that to 0. If you now open this bracket or you expand, we have 3 times 4 is 12, 3 times negative lambda is negative 3 lambda, lambda times negative lambda times 4 is negative 4 lambda, negative lambda times negative lambda, positive lambda squared minus 2 is equal to 0. Now let us write, starting the highest power of lambda is lambda squared. You have negative 3 lambda and negative 4 lambda, which is negative 7 lambda. We also have 12 minus 2, that is positive 10, equate that to 0. We now need to factorize this equation, the characteristic equation, so that we can get the values of lambda. This would be, we need to get the product here. The product is 10, the sum is negative 7. So we need two numbers that we can multiply, this 10. We need two numbers that we can multiply to give us 10, but when we add them, they give us negative 7. These numbers appears to be negative 5 and negative 2. Because if you multiply these two, they will give you positive 10. If you add them, they will give you negative 7. We can now go ahead and factor out. So we have lambda squared minus 2 lambda minus 5 lambda plus 10 is equal to 0. We can factor out lambda here to get lambda minus 2. We can factor out negative 5 to get here lambda minus 2 is equal to 0. Now we can say lambda minus 2, lambda minus 5 is equal to 0. If you have two numbers and when you multiply them they give you 0, it means either of the two numbers could be equal to 0, which means lambda minus 2 is equal to 0. That gives us lambda 1 is equal to, let me write this with a different color. This will give us the first value of lambda is lambda 1 is equal to 2. Then we have lambda minus 5 is equal to 0. The second value of lambda 2 is equal to positive 5. So here you can conclude and say lambda 1 is equal to 2 and lambda 2 is equal to 5 are the required eigenvalues. They are the required eigenvalues. The eigenvalues, you also call them the characteristic values or latent roots. Having obtained the eigenvalues, we are now going to say substituting the eigenvalues substituting the eigenvalues in a minus I lambda x 1 at a time, we get. So now we need to get the eigenvectors. To get the eigenvectors, we are going to substitute the various eigenvalues we have obtained in this equation. So you have a minus I lambda is equal to 0. Here you ought to have equated this one with equal to 0. Equating that is equal to 0. So we already have a matrix A. No A is a matrix 3, 1, 2, 4. The square by square is a 2 by 2 matrix or square matrix. We have our first value of lambda, or the characteristic value, or the eigenvalue is 2. We have x. Cx is a column matrix or a column vector, is equal to x1, x2. X is a column vector or a column matrix. So now we can write everything in matrix form, and we can say 3 substituting in this equation 3 1 2 4 minus the identity matrix times lambda, but lambda is equal to 2 1 0 0 1, all these multiplied by the eigenvector x. So we need to multiply with the eigenvector x. x1 x2 is equal to 0. So you also need to write 0 in matrix form. Let us now simplify this bracket. We have 2 times 1 is 2. Then we subtract from 3. So we have 1. 2 times 0 is 0. Subtract 0 from 1 is 1. 2 times 0 is 0. Subtract 0 from 2 is 2. 2 times 1 is 2. Subtract 2 from 4, this is 2. Multiplied by the eigenvector here, which we are about to find, or whose value we want to determine. It is x1, x2. Then we equate this one with 0. If we now do matrix multiplication so that we can rewrite this equation this matrix equation in equation form or in algebraic form. Remember, when you're doing matrix multiplication, it is low column. So it is x1 times 1, it is x1, plus x2 times 1, it is x2. That one is equal to 0. Then we got the the second low, multiply with the column vector. It is x1 times 2, 2x2, 2x1, x2 times 2 plus 2x2. On the other side, we are equating with 0. We have two equations, two algebraic equations or two simultaneous equations. These equations, we use them to get the values of x1 and x2. And notice, those two of them, they are equal to 0. It's not possible for us to get the value of x2 and x1 in terms of constants. We can only write them as a relation between the two of them. We say x2, we write it down here, x2, take the x1 to the other side of the equation, is equal to negative x1. We can say the first eigenvector x1 is equal to, because is the eigenvector corresponding to eigenvalue lambda 1, we call it x1 is equal to x1 x2, that we have just seen, x2 equal to negative 1, x1, but x2 is negative x1, or we can say this is equal to x1 1 negative 1, but to be more general, we are going to say x1 is equal to a constant beta 1 negative 1, to be more general, where this value could be any constant like 2, 6, 10. The eigenvector will take many different values. That's why we are putting it in a more general form. We now determine the second eigenvector. We can say for lambda 2 is equal to 5, we have a minus I lambda x is equal to 0. We know A is a square matrix, lambda is a second eigenvector, and x, we have seen x, or the eigenvector, is a column matrix. And therefore we are going to say we have A is 3, 1, 2, 4, minus the identity matrix multiplied by lambda. We can start by writing the value of lambda. We can start by writing the value of lambda. Lambda is 5. This is 1, 0, 0, 1. All this multiplied by the column vector x, which is x1, x2. All these we are equating to 0. We also write that one in matrix form. If we now do the subtraction here, you get is 1 minus, negative 5 times 1, that is negative 5. Or simply 5 times 1, 5, minus 3 is negative 2. 1, 5 times 0, 0. Subtract that from 1, it is 1. 5 times 0, 0. Subtract that from 2, it is 2. 5 times 1, that is negative. 5 times 1, that is 5. Subtract that one from 4, it is negative 1. Multiply this column vector x1, x2 is equal to 0, 0. If we now rewrite that in algebraic form by multiplying the two matrices, we will have, taking low column, let's do the matrix multiplication. It is x1 times negative 2, negative 2x1, 1 times x2 plus x2 is equal to 0. We have x1 times positive 2, 2x1, and x2 times negative 1, negative x2 is equal to 0. Using either of these two equations, notice if you use either of these two equations and you write x2 in terms of x1, you get the same result. Because if you use this one, this x2 is equal to positive 2x1. If you use this one, is x2, again it is x2, x2 is equal to 2x1. Both of these equations should give you the same result if you are to write x2 in terms of x1. If they are not giving you the same, if they are not giving you the same result, you must have made a mistake somewhere, and therefore you should check where you went wrong. Now we can say x2 is equal to x1, that is x2. So the second eigenvector, or the eigenvector corresponding to eigenvalue lambda 2 is equal to 5, we are going to say that eigenvector is x2 is equal to, as we have said earlier, x1, x2. But you have seen x2 can be rewritten in terms of x1 as 2x1, or we can say x1 is equal to 1, 2. But we like to be more general and we say x2 is a certain constant, say alpha 1, 2. Because this value will take many different forms. It could be 1, 2, 3, 5, or 10. It will go up to infinity. And therefore, the required eigenvalues and eigenvectors are lambda 1 is equal to 2. We have x1 is equal to, that one was 1, beta 1, negative 1. We have lambda 2 is equal to 5, and we have the second eigenvector is equal to, say, alpha, which is 1, 2, 1, 2. This is one of the topics that will give you the marks that you need to pass in that exam in the shortest time possible. So I suggest in the examination you should always make an attempt of starting with this topic, and then you move on to a little bit more involving topic. You can continue watching more videos now.